Okay. Oh, I noticed that my sound is off. Oh, it's okay. Okay, so today I want to talk about, generalization fibrations from groupoids to categories, and maybe we will even have time to talk about entopoia, but I'm not sure. Okay, so basically, last 2 times we discussed in detail how we can construct Postnikov towers for groupoids. And it would be nice if we could do something similar for arbitrary infinity or n categories. So to this end, I will first start with discussing enrichment and Posets, and then we will discuss fibrations and categories and stuff like that. So let me start from okay. So first of all, a very standard definition. Category enriched over monoidal category V is first a collection of objects second for any 2 objects the object of homomorphisms. So in ordinary categories we have enrichment of over sets, so we get a set of morphisms between 2 objects, and here we get an object in V. Third, it's composition. So this is where we need the monoidal structure in category V. So we have composition. And finally, we should have unit associativity, etc. So basically, the idea is that we replace monoidal category of sets with monoidal category V. We require all the same things that we require for categories. So of course, we're talking about weak enrichment. Meaning that we only consider identities up to higher morphisms. So that means that, for example, for associativity, we don't necessarily require that it is strictly associative. We just require that there is a higher morphism, which makes this diagram compute. So yeah, like this. Okay, so let's have a few examples. One categories or just categories. is the same as set enriched categories. Weak two categories is the same as weakly enriched over categories. Finally, weak three categories is all the same thing, but now we're enriching over two categories. So that's the same for the same thing, weakly enriched over. So weakly, I'm sorry. So weakly enriched over weak two categories. Okay. So morphisms between such objects is V-enriched functors. V-enriched categories is a function. So function, of course, it may be a function between classes. We don't mind such things. The function on objects and for any pair of objects in E, we have a V-morphism Okay, and so of course we also have a factoriality condition. So yeah, we of course have a weak factoriality condition. So yeah, those are V-enriched functors. Sorry. Okay. So let's consider an example. Consider -2 enriched category. So we remember that -2 category is in fact just a point. So this category should not be very interesting, but in fact, we will have something. So it's a collection of objects. So collection of objects plus between any two objects a unique isomorphism. So since this collection might be empty or at least one object. If this is empty, this category is equivalent, of course, to an empty category. And if there is at least one object, then this category is contractible. So it is equivalent to one point category. So actually, it's very nice because we just showed that each -2 enriched category is a -1 category. So we actually shift up our hierarchy of categories. And that's very nice. So we get any -1 category in this way. So -1 categories just mean -2 enriched categories. So that basically gives us an idea how to construct n categories, but we will see a bit down the road that actually there is a whole plethora of ways to construct infinity categories, and it basically depends on the way you're taking a certain limit. So we don't have a unique infinity category, a unique notion of infinity category. We in fact have infinitely many different notions of infinity category. Okay. So now another example. We may now consider enrichment over -1 category. So for any x and y in C, we get hom of x and y is either a lie or a truth, which corresponds to an empty set or a point homotopically. And for any x, y, and z, we have there is composition which can be very naturally interpreted as conjunction. So that's just conjunction. And actually, if we interpret this, so if we have a morphism, well, if our hom xy is this truth category, then we can interpret it as x being less or equal than y, and we get a poset. Of course, this is not a strict relation, but this is what we get if we don't impose any equality conditions. So it is natural in higher category theory to consider everything up to equivalence. And here we can't really say that two objects are equal, but we can say that they're equivalent, and they're equivalent precisely when x is less or equal than y, and y is less or equal than x. So x is equivalent to y. So yeah, we get a poset, and this, in vein of the previous example, we actually can think of a poset as being zero category. And usually we think of zero categories as just being sets, but actually somewhat more natural understanding of zero categories is posets. So zero category. So not sets, Posets. And so we can construct the following enrichment table. We had previously periodic table, but now we will have another table. So we start from the trivial -2 category. Then we have -1 categories. Those are just two possible categories, a lie and truth. So we have an enrichment morphism. Sorry. So yeah, enrichment goes this way. So then we have posets. In posets we have sets. Actually, I think we should have something here, but I don't know what it is. So maybe we don't have, I'm not saying that, well, the authors don't claim that we have something here, but I guess we should have something here, but I don't know what it is. So let's just leave a question mark here. Maybe someone will figure out this later. So then we have enrichment and we get 2 posets, or this is similar to categories being enriched over posets, then 3 posets and so on. Here we have 2 categories. Here we have categories. Here we have sets. Yeah, so categories are just categories enriched over sets, so that checks out. I'm sorry. Yeah, no, it's okay, yes. So then we have groupoids inside of categories. Then we have locally groupoidal to categories. So those are just categories which are enriched over groupoids. Then we have 2 groupoids, and so on. So we have enrichment in this direction. Yeah, and so basically we get infinity groupoids if we go over the diagonal of this thing. So if we go over another diagonal, we will get infinity 1 categories. So if we start from, where should we start? Wait a second, we should start from N. So we should start from 1 category. So we should start from also from groupoids. Then wait a second. No, we should start like this. So if we go like this, we start just from regular categories where not necessarily all 1 morphisms are invertible. Then we go by diagonal like this. We will get infinity 1 categories. And so on. So there are different ways to get an infinity category. We also can go this way and get infinity posets, and that's another kind of infinity category. It's completely justifiable to do it like this. Okay, so and this poset is characterized by the fact that we have this table is characterized by the fact that we have n plus 2 invertibility levels at the row n. So that's why we should have something here. I guess maybe it's just 2, which yeah, but I'm not sure. Okay, so we have this table, and we can glue it together with the periodic table of categories, and we will get a 3-dimensional table. So, which explains somehow the connection between monadality of categories and enrichment. Well, yeah. So now I want to give another motivation. So remember that we had a Postnikov tower like this. So we started with some morphism P. And we ended up with the point. So we had something like this. But we had all we had then were group points, so it was much easier to do. So this one should be 1, 2 surjective. This should be 0, 2 surjective. This should be 0, 1 surjective. So in E1, we identified parallel. I'm sorry, that's not E1, it's E-1. We identified parallel morphisms in E0, and we got ourselves a poset. Why? Well, simply because if we identify parallel morphisms, we may end up with possibly 2 things: an empty set or a set which consists of 1 point. So for arbitrary categories, E-1 is a poset, E0 is a 2 poset, and so on. Yeah, so that's another justification that for arbitrary categories, construction of the Postnikov tower implies that we actually should have posets and poset enriched categories instead of just regular categories and categories enriched over categories as we think usually. Yeah, so that's another reason. Okay, so I basically explained where the posets come in. Now I want to say something about fibrations for general categories. Okay, So first of all, let's consider an example. Consider a functor from a billion groups. Then the preimage of this functor is a category of all a billion groups equivalent, well, isomorphic to G. So this thing right here is either an empty set or a point, because all of them are isomorphic, or there are none, because the group is either a billion or not. So P minus 1 of G is a -1 category. So similarly, if we have an equivalence, then P minus 1 of P is equivalent to a point, which is in turn a -2. So this leads us to some pretty, well, pretty natural conjecture. But I think I'll formulate it in just a moment. First of all, I'll consider, yeah, so first of all, some a conjecture, then we'll consider another example. So conjecture. Functor gets purely J stuff. If its preimage is category when categories. Let's consider another example. No, I don't think that's right. So no. Wait a second. No, I think no. This is clearly wrong. So it's just an N category. Let me check it real quick. I think that this should be more reasonable. Yeah. So preimages are N categories. Yes. Okay, so another example is that we can consider a forgetful functor. Yes, there is some question. What is J? What is J? J is some index, which is not related to N, incidentally. Thank you for the question. So it forgets N stuff precisely. Yeah. Thank you for the question. Yes. The answer is N here is the same as N here. There should be no J. Okay, so let's consider a forgetful functor from groupoids to sets. So if we take pre-image of set of on 4 elements, then we'll get 2 groups. And let's think about, so that's up to equivalence, of course. So this is just a set. This is a set. Since homomorphisms, morphism, which is a bijection, is an isomorphism. So yeah, so that's a specific property of groups which allows us this consideration that actually for groups we don't get any higher structure because sets completely determine morphisms between groups. And so when we say that we have something up to equivalence, it actually means that this is the same equivalence as in sets. So that's why it is just a set. But now I will consider another example where we get some higher structure. So we can consider a similar functor from topological spaces to sets. Then, so that's just a forgetful functor. Then p minus 1 of 4 is a poset. Why is this true? Well, just because we have different topologies on sets of 4 elements. So, for example, we have this weakest possible topology, anti-discrete topology. Then we have various, so don't worry, I won't draw them all, but I'll draw some. So then we have various topologies like this. I draw open sets, of course. So yeah, we have such topologies, and then below them we have topologies with sets with open sets consisting of 2 elements and so on. So yeah, and so they form a poset. That was the point of this example, that for some functors that forget more than just structure as it was with groups. So here we just forgot structure and we did not lose that much. We still got a set. Of course, for a more complicated set, we may have a lot of different groups, but the point remains that it's just a set. We don't have any relationship between its elements. But for topological spaces where the points don't determine the space, we actually get an entire poset of possible topological spaces in the fiber of a given set. So yeah, that was the point of an example and illustration to this conjecture. Okay, let's consider one more example, even higher nature. So we have a functor, forgetful functor from monoidal categories to just categories. So fiber over category C is an object. I will specify its nature in just a moment. It's an object of possible ways to endow C with monoidal structure. So we want to show that the fiber is in fact a two-poset. Let's understand this. So assume that we have C and C prime inside of this pre-image. Then morphisms are functors. That is still monoidal functors. And between them, we have natural transformations. So these transformations are, they either exist or they do not exist. So this is an enrichment over category consisting over only of two elements. So these transformations this they're unique. Really not. Thus, we get a category which is enriched over -1 categories. -1 categories enrichment. So this is -1 category enrichment is just between two functors. So after considering the whole fiber, so yeah, just the home object is just a category of -1 categories, and the whole fiber is thus a two-poset. So the home object is a poset, and the whole fiber is a two-poset. Okay. Let's consider another example. So assume that we have a good category to enrich over. That means that we have a forgetful functor from V enriched categories to just categories. So objects of C0 are just the same as objects of C, and morphisms of C0 between X and Y are just morphisms, set of morphisms in V from a fixed object I to this object in V. Okay. So now I think before discussing this example in more further detail, I think it's a good time to make a 5-minute break. And then I will continue from this example. Okay, so a good example of such categories are, for example, topological spaces, simply set, simply show sets, just categories. And so in this cases, our functor is zero surjective. Over groups. Yes. Thank you. Over groups, however, so sorry, over abelian groups. It is not true. So if we consider just a functor from abelian groups to groups, we don't get a zero surjective functor since not every group is abelian, of course. And if we consider a functor from abelian groups to from categories enriched over abelian groups to just categories, we get, so we have this functor, and we will get a functor from abelian categories to just categories, and once again it is not surjective since not every category can be made abelian. Another another well-known fact. So in general, this functor is not one surjective. Since not all functors admit enrichment. Obviously, it is not necessarily too surjective. Since not every natural transformation admits enrichment, and so on. Okay, so however, we have a large class of examples where the functor is in fact zero surjective. So if this functor is faithful, then this zero is surjective. Okay. I also note that, functor is always 3 surjective, since any functor is 3 surjective. Yeah. Okay, so we're interested in the following question. How does the following fiber look like? So we have a category, we have a fiber, how does it look? So objects are enrichments C. Morphisms are the functors such that the value of this forgetful functor is identity. So two morphisms are natural transformations with identity components. So this natural transformations just assert that two functors are equivalent, and so the fiber in general just one category. So this is completely justified, since we forgot a lot of things when we forget enrichment. But if the functor faithful, then the functors are completely determined. By their set theoretic image, by their image in categories. So thus the fiber is just a poset. So we have natural transformations between functors, and those are morphisms, and transformations between them are just sorry. No. Functors are objects of this fiber, and transformations between them are either there is a transformation which asserts equivalence, or there is no transformation, so it's a poset. Yeah. Okay. So let's consider another example where we get so much stuff that it actually shows that the functor is very, well, it forgets a lot of things. So example where we get even higher stuff. So consider a forgetful functor from pairs of categories to categories. So a pair of categories is naturally a category. And so the fiber is a two category. Well, since the fiber is just a category of categories, so it's a two category. And the functor is not surjective. J less or equal to 3. So our definition of functor forgetting k stuff should be like this. Sorry, one moment. So the functor forgets stuff. Subjective. Both dimension k. Okay. So that was basically our conjecture that the fiber of a functor that forgets purely J stuff is a category of J category. So maybe it's somewhere here that should be -1 subjective about dimension J plus 1. I think something like that. But in general, the idea is that we can characterize the functor by the way that it forgets or does not forget some things. And this can be in turn characterized by the fact how large is the fiber. So if the fiber is a poset, for example, this functor does not forget that much. Or if the fiber is set, the functor forgets only maybe structure. But if the fiber is, for example, like here in this example with categories, is an entire two category, that means that actually the functor forgets a lot of things. Okay. So that's basically the question that I'm going to ask right now. We use similar reasoning. To group words to categories in our characterization of functor that forgets J stuff. So the answer to this question is sometimes. Let's describe the cases where we can do that. So first of all, if the functor is an equivalence, all fibers are -2 categories, which are contractible. So we have two kinds of -2 categories, an empty category and contractible. And so if it is an equivalence, it asserts that fibers are all should be contractible. That's reasonable since, well, it is an equivalence, and for each object we should have, well, up to isomorphism, we should have some object in a fiber which is under this functor equivalent to this given object in the base. Okay, so that's the first one. The second one, if the functor is fully faithful, then it is almost like an equivalence. In fact, it is an equivalence on its image, which is characterized by the following. All fibers are -2 categories, meaning that they're either empty or contractible. Okay, if the functor is faithful, then all its essential fibers are posets. And finally, for an arbitrary functor, the fiber is arbitrary. So we can find a functor with the arbitrarily bad fiber. Well, not bad, but arbitrarily large fiber or something like that. So we would like certain assumptions which allow us to invert these assertions. And this is actually possible. It's called categorical fibrations. And I will describe it as that right now. Okay, so let's, I want to say what we want. And reverse statements. So the first possibility which we can use is that if both E and B are groupoids, then inverse statements hold by our previous discussion. So we discussed how to what conditions may be imposed on a functor between two groupoids, which asserts that this functor is, for example, an equivalence or a fully faithful functor. So yeah, And the second one is that, well, the categorical fibration. So I won't give a precise definition, but I will try to explain what it's about. Okay, so we have a functor from E to B. Categorical fibration if for any arrow in B there is a universal lift to E. Universal meaning that, well, that actually if we have an arrow in the base, then we can transport datum in E along this arrow. So yeah, that's the idea of categorical fibration. Now let's consider an example. Since I did not give any definitions, we can start from examples right now. So let B be a category of rings with morphisms between them, ring homomorphisms. And let E be a category where objects of E are pairs, where R is a ring and M is an R module. And morphisms between them are the following. So Rm to Sn is a pair F phi, which works like this. So F from R to S is a ring homomorphism. Phi from M to N is an F equivariant map. F equivariant morphism of modules, meaning that the following formula holds. So F Rm, or R belongs to R, is the same as F of R times phi of M. So that's the category, and we have categorical fibration. Let me show how it works. So we have this functor, obviously, which just forgets the second component. And if we have a morphism in the base, lift, which will be denoted like this, and well, it works in a reverse direction. So we obviously have a map from, yeah, so we obviously have a pair R F upper star N, and the morphism from F upper star N to Sn. So it's something like this. So obviously, yeah, obviously we know how R epsilon R epsilon N. It's just F of R on that. So as an abelian group, it's the same thing, but with a different ring structure, a ring action structure. So when we have a transport like this in the opposite direction, that's a categorical fibration. So and if we have and transport in the same direction, it's called cofibration. So for example, here we actually have both. We can also define the F lower Schrick of M module, which is just a tensor product. Looks like this. Okay. So another, well, another reason for good properties of fibrations is that allows for application of the main principle of the Galois theory. So we established earlier that in topology, the main principle of Galois theory looks like this. We can classify all coverings of a given base by functors to sets. So here, instead of functors to sets, we may classify all fibrations by functors from base to category of all categories, of all small categories. Okay, so that's the definition of fibration. And now I can formulate a hypothesis. Which relates all these things and explains why we need fibrations. Well, I sort of explained it earlier, but now I will give a hypothesis which mentions fibrations and gives the reason behind their existence. So if a functor between two n categories forgets it most. And stuff. Then the fibers are n categories. The converse holds for n fibrations. So n fibrations are just fibrations in n categories. So instead of a lift of just one morphism, we should have a lift of all higher morphisms as well. That's just that. Okay. So I think we have some 10 more minutes, and I can briefly explain topos theory. I think it's an appropriate amount of time to explain all of topos theory. So, and to play. First of all, yes. Okay. Okay. So first of all, a definition of a topos. So it's rather should be called one topos. I won't explain the whole topos theory. I will just explain lower topos theory, I think. So one topos is a category such that there are all limits and co-limits by complete category. It is Cartesian closed, meaning that there are all home objects are in the same category and exponential objects are also in the same category. And finally, there is a sub-object classifier. So we will talk about it in detail when we deal with Tapoya, but now it's sort of a quick preview of the program. Finite sets is not a one topos. Well, I think that if you require only finite limits and co-limits, then it is one topos. But well, if you require all limits and co-limits, which is the case for sheaves, then finite sets is not one topos. Well, that's just actually, I think that there is a statement that sort of finite sets are somewhat unique in their position. So they're like the only well, sort of that this situation does not occur anymore. So if we choose different axioms like the ones I wrote down, then we will get all the same Tapoya except for finite sets. So yeah, in short, the answer to your questions, finite sets is not a one topos in this definition. And all sets are topos. Yes, 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 yes. That's basically an idea. So Tapoya emulate the category of sets, and that's basically the idea. It's one face of a notion of a topos. There is also a topological interpretation, but from a logical perspective, yes, topos is just a universe of sets. So that's what I was about to write down. So topos is generalized universe of sets. So in the same way, NM topos should be universe n-1, m-1 categories. And also, let me note that since N0 are groupoids, and we may want to try this construction on groupoids, but the only groupoid which is the topos is the trivial one. So that's not very hard to prove, but you just think of it like this, that if you have an exponential object, then it should lie in a certain component. However, and it should be isomorphic to some object of the groupoid, or it should lie in its own separate component. In the first case, we have an obvious contradiction of Russell type, and in the second case, we have well, we don't have any morphisms from the exponential object, which is very strange, because we always have this evaluation morphism. So groupoids are bad topoi, and we don't have any groupoid topoi. Okay, so what is 0,1 topos? It should be a universe of truth values. And it turns out that actually this thing is, we will also talk about this, but let me introduce the concept. Actually, this is a Heyting algebra. So the conditions is that, first of all, by completeness forces. So it's obviously a poset, of course, but it forces this poset to be, well, by complete. Such posets are called lattices. So this is not only a Heyting algebra, it's complete Heyting algebra because of this bicompleteness assumption. But also there should be this condition which makes up a Heyting algebra, is that, well, we have this, so we have a poset, and thus it makes sense. However, here, if we define the negation operator like this, so if we define the negation operator, I'm sorry, yeah, we define like this. Then what we get is precisely, we don't have the law of the excluded middle, so this is not equal to A in general, and that implies that Heyting algebras are models. Heyting algebras are models of the intuitionist deterministic logic. So in particular, models of classical logic, which are called Boolean algebras, are a subset or subclass of Hating algebras. And these objects may seem strange, specifically because we did not sign up to study like logic or mathematical logic or something like that. But actually, Hating algebras are natural. Hating algebras natural. They come from topology. And the fact of the matter is that actually, given a topological space X, its category of open sets forms a Hating algebra. And so if we have a function between topological spaces, then we have a function on Hating algebras in the reverse direction, which just takes the what happened, which just takes the preimage of a set. And so that's the natural reasoning behind the existence of Hating algebras. And so this gives us the second phase of topos theory. The second phase of topos theory, topos is a generalized topological space. And also I have to note that, well, we can just throw out the usual topological space, which consists of points, and we say that local is a Hating algebra regarded as a topological space. So the theory of local is basically an analog of theory of topological spaces, but which does not use points. So we can still construct shift theory, of course, but we now don't need any reference to points of the topological space. And this is sort of nice. Okay, I think that I will finish my talk here. Let me stop the recording.